Hey folks, I'm going to be going over lesson 4 in matter and energy with you. So this is posted in Google Classroom as your PDF notes as usual. So for this lesson, we're going to be looking at changes of matter, and those changes can be chemical changes or physical changes. And we're also going to look briefly at the law of conservation of matter and energy in both types of changes. So first off, we're looking at physical changes. So in physical changes of matter, you have a change in appearance, but you do not have a change in the chemical composition of the matter. So basically, let me see, chemical composition. The formula of what you're working with will stay the same. It's just the particles in your sample will be arranged a little bit differently. So easy example of this would be a phase change. We're not making anything new here. No new substance, no new friends, no new substances. We just have a new rearrangement or a new arrangement. So in this example of the ice melting, we went from solid water to liquid water. So in solid water, the particles are arranged in a nice pattern, and in liquid water, they're free to move around each other. But this H2O formula has not changed. We're just taking those hydrogen bonds that hold the water molecules together, and instead of having them locked in place, we are loosening them up. So examples of changes that are physical would be any sort of change in phase or state. So think physical phase. Phase changes are physical changes, really important. This shows up a lot. So anything that you're doing with boiling, freezing, melting, any sort of phase change terminology, and we'll go over those in more detail, that's a physical change. Some sort of change in appearance, like dissolving, would be a physical change. Changes of shape. So if you were to hammer something into a sheet, or if you were to draw it into a wire, so metals, malleable and ductile, that would be changes of shape. Or even something that's brittle. If you hit it with a hammer and it shatters, that's a change in shape, but you're not changing the formula of the material you're working with. And then changes in size, if you were to cut it into pieces or grind it into smaller particles. For chemical changes, we are going to have changes that happen at the particle level. So our formula of our materials will change, and the composition is entirely different after the change. So we have new formulas, and I'll give you some examples of that. So entirely different. So this is an example of a chemical change. We have a nail rusting. So, once that iron is converted to rust, you don't have iron anymore, you have iron 3 oxide. This is an example of an alkali metal, so something like potassium in water. And I showed you this with sodium in water, that you no longer have the sodium, or you no longer have the potassium, you have a new compound formed. So that's new substance. So you have new formulas. I think more, there we go. And we can only really reverse these with another chemical change. So contrasting these bottom two equations with the water change from earlier, when we were looking at a phase change of water, let's say I'm going from ice, solid water, to liquid water, I'm still dealing with H2O. I'm just changing the phase marker at the end. With these examples, especially this one, I'm starting with liquid water, but then I now have hydrogen gas and oxygen gas. So in a change like this, a chemical change, I'm actually, breaking bonds that are making the molecule the molecule. Examples of this, if you see something that mentions burning or corroding, corrosion, combusting, decomposing, rust or tarnishing. If you have silver jewelry that has tarnished, it's no longer silver. The silver's been converted to something called silver sulfide. We will actually later this year take silver jewelry that's tarnished and we will reverse the chemical reaction, but it's a chemical reaction that needs to be reversed. It's not just a physical change. In both chemical and physical changes, we also will have changes in energy. And we've looked at these terms before. So if the change emits, and remember the word emits means releases. If you have a release of energy, it's called an exothermic process. So exo, exit. What it would feel like to the touch if you were doing a reaction in a test tube or in a beaker and you were holding the sides of that test tube or beaker, it would feel warm to the touch because the energy is being transferred to the surroundings, and that the surroundings would be the test tube or the beaker. So that could be a temperature change that you'd feel on your hands, or if light is given off during a process. And I showed you that when I did, I think it was the calcium and sulfur in the test tube in the fume hood. When I heated that up, that bright light, that glow that came off of it shows you that that process was exothermic. It's giving off energy. And the way that that would be shown in a chemical reaction is that the word energy, or a physical change. So physical changes can be endo or exothermic as well. So in any change, if I'm dealing with an exothermic process, whether it's physical or chemical, the word energy would be written on the product side because it's showing that it's being released at the end of the process. There's both chemical and physical changes involve those changes in energy. So if it absorbs it, it's the opposite of an exothermic reaction or exothermic process, which means it is endothermic. So endo, enter. So the process requires energy to be brought in from the surroundings in order to trigger the process to occur. So this example here, if I want to take ice and melt it, it makes sense. I need to add energy to that system. Energy needs to go into the ice to get it to change into liquid water. And if I reverse this, if I took liquid water and wanted to freeze it, I would have to release energy to the surroundings to change it from a liquid back to a solid. So this is an example of a physical endothermic change, whereas, let me write that down. So this one from the prior slide is a chemical exothermic, and this one is a physical, and I know it's physical because I have the same formula on both sides as physical and endothermic. The last thing to address here would be the conservation of materials. So conservation means I want to save something or maintain it. So during all physical and chemical changes, mass is conserved. So what that means is matter cannot be created or destroyed. So whatever pieces, whatever atoms or molecules I had at the beginning of the process, I need to have that many at the end of the process. They'll just be converted into a different form. So if it's a physical change, it might be, just change of phase, but I'd have the same number of molecules. Or if I hit it with a hammer, they're just spread apart now. But if it's a chemical change, same deal. I would just be taking those same numbers of atoms and molecules and rearranging them. So this would be an example of conservation of mass type of problem. 35 grams of liquid water are evaporated in a closed container. How many grams of water vapor will there be when the process is done? Well, if I'm going from liquid water, so if I was looking at this as a particle diagram, liquids are kind of jumbly, they're touching each other, but they have no real orderly arrangement. So if I have 35 grams in my container as a liquid and I vaporize it, I'm still gonna have 1, 2, 3, 4. I happen to draw 12, so I wanna make sure I draw 12. 9, 10. Okay, I would still have 35 grams at the end. All we're doing is spreading them apart. So it would be like if I, had all of you in your desks seated, and then I said, okay, now stand up and walk around. I didn't lose any kids in the process, I hope, right? No one fell out a window. You can also see this with chemical reactions. So magnesium metal reacts with oxygen to form magnesium oxide, how will the mass of the magnesium oxide compare to the combined masses of the magnesium and the oxygen that formed it? So if we think of this like a word equation, it's like math class. Magnesium plus oxygen forms, that arrow means forms or produces or yields, magnesium oxide. Well, the mass of the magnesium oxide, that total mass would have to be equal to the components that made it up. Otherwise, where are you getting the extra stuff? You know, we can then represent this with a chemical equation with correct formulas, and we will talk about how to write these chemical equations and balance them to show the conservation of mass. So you can see here 2 magnesiums on the left, 2 oxygens on the left, 2 magnesiums on the right, and 2 oxygens on the right. So we will get into that later on. Here's another mathematical example. If 40 grams of substance A are reacted with 20 grams of substance B to form substance C, what will the mass of substance C be? So this is a math problem. It's addition and subtraction. So here's my equation. Substance A reacts with substance B to form substance C. 40 grams plus 20 grams equals X grams. So 60 grams would be the mass of substance C. This is a multiple choice question. This was a Regents question. Which process results in a chemical change? So a chemical change, we want to think about words that indicate we're changing into a completely new substance. Okay, so am I tearing tin foil apart, melting an iron bar, crushing an aluminum can, or burning magnesium ribbon? So tearing foil, if I have a piece of foil and I start ripping it, it's still foil. It's just smaller pieces of foil. Melting, that's a phase change. So remember again, phase change is a physical change. So that's not going to work. Crushing an aluminum can, it's still an aluminum can in a different shape. But if I burn magnesium ribbon, that word indicates that we have a new material by the end of the process. And lastly, here's an equation with that same magnesium and oxygen, but using numbers here. Based on the law of conservation of mass, predict the minimum amount of magnesium that will react with all 16 grams of oxygen to produce 40.3 grams of magnesium oxide. So I'm just going to put the numbers up above the substances in the equation. So it's telling me 16 grams of oxygen, and it's telling me I've produced 40.3 grams of magnesium oxide, and it's asking, well, how much magnesium would it take to get me there? I'm just going to put the symbols in for the operations. The plus sign is still a plus sign. The arrow is like an equal sign. So when I solve this and I subtract 16 from both sides, the amount of magnesium would have to be 24.3 grams. Okay, so in this lesson, you've seen the similarities and differences between physical and chemical changes. We've looked at some different ways to identify if a change is physical or if a change is chemical using words, pictures, and equations. We've also looked at just briefly terminology for changes in energy and the idea that we have to end up with the same amount of matter that we started with in any sort of physical and chemical change. Thank you for following along. Please submit your completed notes.